Hello and welcome, class, as we continue in through Chapter 11 and all of our studies of the properties of gases, how they function, how we can measure them. Today we are going to be talking about partial pressures. So in our last lecture, we introduced all of the early gas laws, namely Boyle's law, Amonton's law, and Charles' law. We also introduced the concept of absolute zero. We are again working roughly chronologically through Chapter 11, and so we're going to pick up with the discovery of partial pressures. What happens when you have mixtures of gases? The scientist who was observing mixtures of gases to try and draw some conclusions about their properties, the realities of nature, was John Dalton. So in our previous lecture, we introduced Robert Boyle, who is namely one of the founding fathers of chemistry. John Dalton is our second. So John Dalton, in studying mixtures of gases, discovered, or rather observed, that these mixtures, much like the atmosphere, formed homogeneous mixtures, despite these mixtures of gases having different masses and densities. So for example, the atmosphere around us contains, again, mostly nitrogen. It's like 70% nitrogen, 20% oxygen, like 10% carbon dioxide. Fourth place is argon, and it's like a fraction of a percent, and then everything else after that's like very tiny amounts. But each of these gases doesn't exist in distinct layers or pockets of space like a heterogeneous mixture would. Each of these gases exists in a homogeneous mixture. And this is true even if you take a vacuumed container and insert gases in by hand. Each of these gases, whether they be nitrogen, oxygen, carbon dioxide, I'm just doing really simple symbols here, each of these things evenly spreads out. It's almost like they don't interact with each other, they also don't interact with themselves. And so he was able to draw that specific conclusion that these particles seem to not be interacting with each other and instead will spread out. We call this Dalton's law, which was published in 1801. So we're kind of backstepping a little bit here in the timeline. Dalton's law came out, it was published prior to Charles' law, but it was also being worked on as a project independently of those other gas laws. So Dalton's law, specifically as stated by John Dalton, states, consequently, when a vessel contains a mixture of two such elastic fluids, each acts independently on the vessel with its proper elasticity, just as if the other was absent. Now that's the Old English way of saying our modern definition that the total pressure, or P total, that is exerted by a non-reactive mixture of gases is equal to the sum of all of their partial pressures, P1, P2, P3, etc., of the components. So let's tie these two things together. I love the Old English wording. Specifically, I want to talk about the word elastic. Now, elastic was a term that was being used by physicists at the time and was one of Newton's terms. To be elastic means that the particle in particular is going to interact with another particle by transferring all energy perfectly. So we can think of this almost like pool or billiards, right? If you shoot the cue and hit, let's say, the one ball, if the hit is perfect, all of that energy from the cue is going to transfer into the one ball, the cue will stop moving, and the one ball will continue along the same trajectory, ideally, right, perfectly with the, like if it were perfect situation, with all of the same velocity, with all of the same momentum, with all of the same energy. So this is what it means to be elastic. We are assuming that there are perfect collisions occurring. So John Dalton was assuming that the particles inside of the gas are interacting with each other as perfect elastic particles. He called these things also elastic fluids, since gases are technically, according to the definition of physics, fluids. They have fluid dynamic properties to them. So these elastic fluids, also known as gases, when put inside of a vessel, interact independently, like again, they're all kind of on their own. They're not forming intermolecular forces. They're not bonding. They are remaining completely separate. And assuming that they maintain proper or perfect elasticity, they're going to just bounce off of each other almost as though they're hitting like the side of the wall of the flask. Like it doesn't, these gas particles don't care about each other. They're not interacting at all. And so the conclusion of Dalton's law is, since each of these particles, let's say nitrogen, oxygen, carbon dioxide, if we're drawing again the parallel to the atmosphere, these things are all acting independently, and the total pressure inside of the container is going to be equal to the sums of each of the individual pressures. Again, because they're not interacting, we're not losing any energy, we're not gaining any energy. The sum of all of our pressures, which is dependent on the sum of all of our individual forces, is going to be a perfect sum and just give us one nice total or additive pressure. All right, this can come in handy when considering that our mixtures are oftentimes not totally pure, because gases can be very difficult to work with. There is always, for instance, water in our atmosphere as well. It may not be as abundant as the nitrogen, the oxygen, the carbon dioxide, but it is there. So a mixture of gases that contains water is said to be wet or hydrous, and a mixture that is devoid of all of the water vapor is said to be dry or anhydrous, which literally means without water. The table to the right gives us a measure for the average partial pressure of water at selected temperatures naturally occurring in the environment. And again, since pressure is related to temperature, since the two are directly related, as we see an increase in temperature, we also see an increase in the partial pressure of water in the atmosphere. And the temperatures that we care the most about, we can see here, are around room temperature, 20 to 25 degrees Celsius. And this is going to provide us with, again, a very small partial pressure of water compared to the rest of the atmosphere, somewhere between 17 and like 24 millimeters of mercury, which again, our standard for the atmosphere is like 760 millimeters of mercury, so this is definitely a small percentage of that. To bring this full circle though, the reason why I am discussing water vapor is if we are working in the lab and we're measuring pressures of gases that are inside of a container, unless we have siphoned out all of the water via chemical means, we're always going to have a little bit of water in there as well. So our measured total pressure is going to be a little artificially high unless we purposefully and with intention subtract out the contributing partial pressure for water. So anytime you're working in a lab, or anytime like in the future you're reading the literature, unless it says that the environment is anhydrous, you can always assume that there's a little bit of water vapor that's getting involved with the chemical reaction in some way. William Henry, who was alive from 1774, so like mid-1700s, all the way through around like the mid-1800s, worked very closely with John Dalton, and specifically his research, like Henry's research, was based off of John Dalton's law of partial pressures. Now we can see that the year that Henry's law was published, 1803, does coincide roughly with the timing for the publication of John Dalton's law of partial pressures, so we can assume, based off of how these two men were seen to correspond, like, through history, text, and publications and stuff like that, that they were probably bouncing these ideas off of each other, and both could reasonably be called Dalton and Henry's laws in tandem. The reason why they're named separately is John Dalton cared specifically about the homogeneous nature of the atmosphere. Henry cared about how gases interacted with other phases of matter. Specifically, he was concerned with how gases would be able to be dissolved into liquids. So he was studying the solubility of gases. And in doing so, he was measuring like concentrations or densities of gas inside of a liquid proportional to the temperature of the gas above the solution. The way that we can think of gaseous solubility in liquids being proportional to the pressure is diagrammed down here below. So let's say there is a closed container. Again, we're working with a closed system here. There is some gas with a pressure up above the surface of a liquid, and there is just some natural amount of the gas that ends up in the liquid down below. Well, if we increase the pressure of the gas, what this means physically is that the gas is going to be forced to interact with the lesser surface more. There's going to be more force applied to this surface, which means that the particles are going to be squished into tighter capacities than what they're probably comfortable with. We're entering a very highly pressurized system. Now, the highly pressurized system means that the gas particles are not just going to be pinging around in the gaseous empty area up above, but they're also going to be forced into the empty spaces, forced into empty spaces of liquid down below, right? A liquid is not perfectly compact. There are still going to be open spaces between the liquid particles as they flow past one another. And so if you're increasing the pressure above the surface of your container, you're also going to be forcing, literally pressing the gas into the liquid down below. Now, Henry's law quantitatively states that the partial pressure of your gas, partial pressure of gas above the surface of a liquid multiplied by what is known as Henry's constant of the gas is going to equal the concentration of the gas in the liquid down below. So the greater the partial pressure, the greater the concentration inside of the liquid. So the greater the partial pressure above the liquid, the greater the concentration of the gas in the liquid. And Henry's constant here is just a proportionality constant. Now we've introduced 3 new laws and observations today, right? There's Dalton's law, Henry's law, as well as the observation that vapor pressure of water is a thing that exists in like closed containers with other gases. And these 3 observations are oftentimes tightly tied together when studying partial pressures of gases over reaction mixtures. So we're going to work through one single example problem today that combines each of these things together, just to demonstrate how tightly knit Dalton's law of partial pressure and Henry's laws really are. What we're going to be calculating is the concentration of carbon dioxide dissolved in a can of Coke at room temperature. Because Henry's law is what manufacturers use, what they take advantage of when bottling up delicious fizzy drinks. The internal pressure of the gas inside of the can is measured to be 380 kilopascals. The vapor pressure for water is 23.8 torr at this temperature, and this number, just to go backwards, I literally just grabbed from this graph right here. So we're at 25 degrees, 23.8 millimeters of mercury, or torr, of pressure. So we'll do that here. And Henry's constant for carbon dioxide at this temperature is 0.034 molarity, moles per liter, per every unit of atmosphere. So the core of this problem is that we are looking for the concentration of carbon dioxide, and we can use Henry's law in order to figure out what this concentration is. However, bear in mind that our pressure provided is over the surface of a liquid. That liquid is water, and water is going to be adding or contributing a bit of pressure to this total pressure. I'm going to let you guys ponder this problem, paying attention to the units, paying attention to the laws that we have talked about so far, and see if you cannot determine what the concentration of carbon dioxide is inside of Coca-Cola. P.S. The values that I have grabbed here, specifically the internal pressure for the can of Coke, is the manufacturing standard at 25 degrees Celsius. So what we are calculating is literally the concentration of Coke in your, or the concentration of CO2 in your average can of Coke. All right, welcome back. If there was any point that you got tripped up while working through these calculations, let's smooth that out together. Let's remove all of those kinks in the understanding, all of those confusions. All right, let's start with this problem by just assigning variables to the pieces of information that we have already. That is going to help us to sort out the information and kind of figure out what we need to do with it. All right, so we're given a temperature of 25 degrees Celsius. Between Dalton's law and Henry's law, there are no variables for temperature really that we need to insert a temperature into. So this 25 degrees Celsius we're going to assume is extraneous information. Now, had I not explicitly listed the vapor pressure for water here, we could have used this temperature to go back to the previous table and find the vapor pressure of water, but the 25 degrees Celsius itself, we're not going to need to use anywhere. All right, we are given an internal pressure of the can. We're going to assume that this pressure, because it's not stated specifically that this is the pressure of carbon dioxide, we're going to assume that this is the total pressure, right? This is the sum of all of the gases inside the can, lending to a total pressure of 380 kilopascals. Vapor pressure for water is also equal to the pressure of H2O. Henry's constant obviously is a kH, so this variable is already labeled for us. Now, in order to find the concentration of carbon dioxide, we're going to need to plug Henry's constant into our equation here, and we're also going to need to find what the pressure of carbon dioxide is specifically. In order to find the pressure of carbon dioxide, we're going to need to make one big assumption, and that is that the total pressure inside the can is equal to the sum of the pressure of carbon dioxide as well as the pressure of water. Could there be other gases inside, like nitrogen or oxygen? Sure. According to the manufacturing standards, though, all of those other gases should be removed. We are solely inserting carbon dioxide, and the presence of the pressure of water comes from the fact that Coca-Cola, which is the same as any other beverage that is a fizzy drink, is made primarily out of water, right? Carbon dioxide is added to the water, flavorings are added to the water, but so long as you have water present inside of the can, there's always going to be a little bit of vapor pressure that is coming off of this liquid. All right, so we're going to assume that the total pressure is equal to pressure of carbon dioxide plus pressure of H2O. So here we could, in theory, just insert our variables, solve for pressure carbon dioxide, plug that on in over here, and then calculate our concentration. But there's a problem. Our total pressure is in kilopascals. Pressure of H2O is in torr. And not only that, but if we observe Henry's constant, we can see that there's a unit of atmospheres present. So what we're going to have to do is pick one of these units and convert all of the other pressure units into that one unit. Now, because Henry's constant has a more complicated unit arrangement, right, it's molarity per atmosphere, I just want to leave Henry's constant alone. And because I don't want to touch Henry's constant, what this means is I'm going to want to convert kilopascals into atmosphere, and I'm going to want to convert torr into atmosphere. Once we have converted our pressures into atmospheres, we'll be able to calculate our pressure of carbon dioxide, plug that into our equation, and find concentration of CO2 in our Coca-Cola beverage. All right, so let's convert our 380 kilopascals into atmospheres first. Now there are 1,000 pascals per every one single kilopascal, and there is 101,325 pascals per every single one atmosphere. All right, so we can convert out of kilopascal into pascal by using a metric conversion, and we can get out of the pascal and into the atmosphere by going back and remembering what our pressure units, or the interconversion between our pressure units is. And this was discussed in the previous lecture, part 1. All right, so the total atmospheric pressure inside of the can is 3.75 atmospheres. So the total pressure inside of that can is greater than the atmosphere around it. This totally makes sense, right? You don't want to heat up a closed can of like whatever fizzy drink you're working with because it can literally explode. Anytime you crack open a new can of Coke, you hear that opening of the can is releasing all of the excess pressure inside of the can. So it makes sense that we are working with a greater atmospheric pressure inside of the can, totally fine. All right, the second conversion we need to do is the pressure of the water, and I'm gonna insert that just down here. 23.8 torr is going to be converted also into atmospheres. We want to make sure all of our units are the same. So there are 760 torr per every 1 atmosphere. And this is the only conversion we have to do since it's a direct conversion. There's no metric prefixes or anything included. The pressure of our water is equal to 0.0313 atmospheres, which is definitely a very small fraction, right? A very small percentage. Compared to the total pressure inside. So these values we're going to insert into our total pressure equation. Our total pressure is 3.75 atmospheres. Partial pressure of carbon dioxide is what we are solving for, and the partial pressure of water is 0.0313 atmospheres. So here we are solving for the other partial pressure, right? The partial pressure of our CO2. We rearrange and find that the partial pressure of our CO2 is equal to 3.72 atmospheres. So it's only slightly less than that of the total pressure. So let's insert that value in for our equation here. The Henry's constant for CO2, 0.0340 molar per atmosphere. And the partial pressure for our carbon dioxide, again, is that 3.72 atmosphere. Our total concentration then for carbon dioxide inside of this delicious beverage is going to be equal to 0.127 molar. Right, so now that we're at 0.127 molar, we could go any directions with this number if we wanted to, assuming we know the volume of the can, which is pretty standard. We could figure out how many moles are inside of the can. We could figure out the mass. We could figure out how many atoms or molecules of carbon dioxide there are. So this information is pretty useful if we want to get a standard for how much stuff is actually inside the can. And that is it for our conversation today. So gas mixtures are actually a pretty straightforward concept, a straightforward thing to work with. Again, remembering that our total pressure is going to be equal to the sums of all of the partial pressures that come or that like maintain it, that contain it, that comprise it. That's the word I'm looking for. As well as solubility. Now you would notice if you want to work through these example problems for Henry's law, being the concentration of our gases times Henry's constant times partial pressure of the gas, that these problems are in chapter 13. That is not a typo. So I did pull a little bit of information from the future. But honestly, the conversation of Henry's law fits so well with our gas law studies. I don't see any reason not to talk about it now, specifically because, again, these two equations, these two laws, work hand in hand. All right, so here we have the example problems, though. I'll leave you to it. If you have any questions and you're in my class, please do not hesitate to email me. Again, if you are not in my class, feel free to drop a comment in the section down below. If you have any homework, do your homework, and until next time, class is dismissed.